In 10.3, we're going to continue our discussion of counting strategies. So we encountered our first counting strategy in 10.2. It's called the fundamental counting principle. And it was numbers of ways when there were separate different options of things we were picking. So we talked about things like choosing an outfit, and among other things. And we related it back to what we had done in 10.1 with systematic listing, about also choosing like the president and the treasurer of a club or something like that. So we're going to continue, and you're going to see some of the things that we have done in 10.2 specifically cropping back up in 10.3. So today we're looking at combinations and permutations, but not in that order. We'll do permutations first. And so the first thing I like to do is just to define what they are and how we compute them. And then we'll talk about how they work inside of problems. So permutation is the number of arrangements of n things taken r at a time. So notationally, you see NPR. So the P, the big P in the middle, is for permutation. The n at the beginning is the number of things we choose from. So n choices, we'll say. And r is the number we choose. So in a simplified way, you could think about our example where we had 6 kids that we were choosing from, and we chose 2 people to be on the committee, or to be the president and the treasurer, or 3 people to be the president, secretary, and treasurer, those kinds of things. So we had 6 we were choosing from, 2 we chose, or 3 we chose. You can also think about this as n factorial on top being the number that we have to choose from, and the n minus r on bottom being the number that we don't choose. Right? So if r is the number we do choose, then n minus r is the number we don't choose to be involved in whatever activity we're looking at. This phrase down here is really, really important. Order matters with permutations. It's different if the president and the treasurer are different people, right? People have different roles. That's a different arrangement of people. So with permutation, order matters. Okay, are you guys ready for combination? Okay, combination's defined slightly differently, and the formula is slightly different as well. This is the number of subsets of n things taken r at a time. So you'll see a C in the middle for combination. The n at the beginning, again, is our number of choices. And the r is how many we're choosing. It's the number we actually choose. And you see the denominator changes slightly. So numerator is the same, still the number of choices, n factorial. The n minus r is down there again, the number of things we don't choose. But we had to also divide it by the number of things that we do choose, r factorial. And in combinations, the order does not matter, and that's really important. So these two calculations are almost identical. They're slightly different with that denominator, but they're almost identical in how we process through them. But obviously they get different answers, right? If you do one versus the other, thinking it's the wrong one, you're going to get the wrong answer. So we have to make sure we're choosing the right one when we're making a choice at the beginning about which of the ones we mean in this particular word problem. So I'm going to show you an example, and it's just a computational example, not word problems, but I'm going to create a context so you can see what they actually tell you after we've made our computations. So we're going to find 12P3 permutations and 12C3 for combinations. So these problems will be almost the same. The combinations one has a little bit of extra stuff in the denominator as we solve it. So my numerator is always the first number that I'm choosing from, 12 factorial in this case. I'll write it out for a few of these for now, but eventually I'm going to actually just do the subtraction sort of in my head. 12 minus 3 factorial is my denominator, but 12 minus 3 is what? 9, yeah. So, basically we're saying we're choosing 3, we're not choosing 9. That's what this means. Okay? So we would write our 12 out till we get to 9 factorial. So 12 times 11 times 10 times 9 factorial over the 9 factorial. And then what we saw happen last time is the 9 factorials cancel. And we'll simply multiply out 12 times 11 times 10. So I won't rewrite the multiplication on this one because it's all still clean. We can see it really easily. What is 12 times 11 times 10?
1,320.
1,320. Okay, is that all right with everybody? Yep, Isabella?
Why did we only put the exclamation point next to the 9?
Okay, so if I were to write out factorials, 9 factorial would be 9 times 8 times 7 all the way to 1. And I'd have all of that on top that matched all that on bottom. So once I get my factorials to match exactly, they both say 9 factorial, I'm allowed to cancel them out because they mean the same thing if we were to continue writing them out. It's just a shortcut notation.
So was it the exclamation point means factorial?
The exclamation point means factorial. All right. Okay, so we're going to do the same thing on number 2, except that we've got an extra piece in the denominator. We've got the 3 factorial that's going to show up here. So I have the same 12 here. I have the same 12 minus 3 factorial here. And I have the 3 factorial. So I have 12 times 11 times 10 times 9, and I have that same 9 on the denominator. And then 3 factorial is 3 times 2 times 1. And I'm writing it out because it doesn't have a matching piece in the numerator, so I need to have all the pieces written out when that's the case. So on this one, if you would like, you can multiply the top, you can multiply the bottom, and you can divide. It's not going to hurt anything, and it would not be the worst thing to do in this scenario. It would be fine. However, if you'll remember from last time, the denominator pieces will always cancel out with something in the numerator. So that's the approach that we're going to see happen on some of our later problems because it's going to be a lot easier to work with in those. So I'm going to model it here too, just for the sake of doing it the same way both times. 3 times 2 is actually 6. So that 6 can cancel with the 12 and leave me with a 2. It's just simplification of fractions kind of step. And if I do that, then I have 12 times 11 times 10. I'm sorry, not 12. 2 times 11 times 10 instead of the 12. And what is 2 times 11 times 10? 220. So let me give you a context thing that kind of describes the difference in what we just found with an example. Let's say you had 12 textbooks or reading books, whatever, 12 books, okay? And you randomly select 3 of them, and then you put them on the shelf, okay? Everybody have a picture of what you're doing? 12 books, pick, and you stick them on a shelf. Okay, so if you don't care what order they're in, that's a combination, and there's 220 different ways that you could have selected the 3 books and put them on the shelf. If you care what order they are in going back on the shelf, that's the 1320, right? So it's different depending on if you put, like the 3 books in a specific order or in a different order. So that's what we're looking at here. The first one is arranging the books in a specific order, permutations. The second one is just selecting them, and they can be in whatever order you want. You don't care. That's combinations. Okay, so when we're looking at our problems, what we're going to have to do is to decide, is it a combination or is it a permutation? Sometimes there's very specific language that'll even say somehow that the order matters. Sometimes you have to read between the lines a little bit. So we're going to take a look at an example, and we're going to decide, is it a combination or is it a permutation? Jeff Hubbard, a contractor, builds homes of 8 different models and presently has 5 lots to build on. And how many different ways can he arrange the homes on these lots so that 5 different models will be built? So we need to decide, does the order matter with the context of this problem? Yes, you're right, Bryn, it does. What pieces of that make you think that's the direction we're going?
There's different models.
Okay.
But I guess that's not really part of it. How many ways can he arrange the homes?
Yeah.
The word arrange kind of implies in order.
Yes, you're right. Oops, I meant to be highlighted. The word arrange implies the order. And this, how many different ways that you mentioned, the number of ways being different also does that. So these are kind of the red flags in this that tell us that the order matters. So you got to kind of look between the lines a little bit. It doesn't say the order matters, right? And in fact, usually it won't. You have to decide if it does or not given the context. So on this one, the order matters. And because the order matters, it is therefore a permutation. Is that all right with everybody? Okay. So I have that notation that has that capital P. How many do I have to choose from? 8. There are 8 different house models. These are like floor plans, like blueprints, okay? 8 different model homes that he could choose from. And how many is he going to build? 5. So as I write this out, this will be 8 factorial on top. And then it's 8 minus 5 factorial on bottom. This is probably the last one I'm going to write that out for. So the denominator is always the subtraction. 8 minus 5 will be my 3. So it's 8 factorial over 3 factorial. So we're going to write out our 8 factorial out pretty far this time. It's going to go all the way written out to 3. So 8 times 7 times 6 times 5 times 4 times 3 factorial. And the 3 factorials will cancel. There's nothing else to cancel in the denominator, so we're simply multiplying 8 down to 4.
Should be 6,720.
6,720 ways. Does that make sense? Okay, let's try another one. This one, a little bit close to home because you guys are taking classes just like Julie is. Julie needs to take 10 electives to fulfill her hours in her degree. I don't know about you, but nobody I advise gets to take 10 electives. So Julie's very fortunate. 10 electives to fulfill her degree, and she decides to start her educational career with electives because she is unsure of her major. If no courses have prerequisites of one another, and there are 17 courses Julie is interested in taking, how many different selections of 10 electives could Julie make? So the first thing we have to decide is, does the order matter with the context the way it's described? You're exactly right. Why not, Ben?
There's no prerequisites.
Okay, it's not because there's no prerequisites, although that would cause problems if there were.
Okay.
It definitely would. There's something else. See it?
The last, the very end.
It is toward the very end.
Many different selections of 10 electives could she make?
Yeah, it's the selections part. It's not how many different ways can she select the courses, right? It's how many different selections could she make. So there's nothing in here that says that she has to make how many different ways that they could be arranged in her schedule, right? There's nothing that talks about in terms of, like taking it one semester versus another semester, anything like that. It's just the selection of courses that we're looking for, not how many ways we could take those courses. Okay? Now, Ben's point about there being no prerequisites is really important because that would cause lots of problems and it might not even allow us to use combinations or permutations if there were some prerequisites involved. So that's being thrown in there to actually eliminate that from being a problem for all of the options. Okay, so we have no order matters. Okay, so the order does not matter, which means we have a what? It's a combination. I'll abbreviate a little bit since I'm running out of space. Okay, so notationally, I have that C notation. How many am I selecting from? 17. And how many am I selecting? 10. So my combination will have 17 factorial on top. And then on the bottom, I subtract. 17 minus 10 is 7. So I have a 7 factorial on bottom. And then I also have, because it's a combination, specifically a 10 factorial on bottom. If it were permutation, I wouldn't have the 10. Yes?
Question, why is the 17 on top?
Because there's 17 courses she can pick from.
Oh, okay.
Yes.
For some reason I got it stuck in my mind, the order of the previous ones where it was like the first number was the one on top, but...
Yeah, so it's not about being the first number. Generally, it's the larger number. So it actually couldn't be switched anyway because it would be smaller. So the first number is always at least as big as the second one. They could be equal. It's a rare case when they're equal.
Okay.
But most of the time, the first one is bigger.
Okay.
Probably, I'll make up a statistic, like 98% of the time. Yeah, that's made up statistic. But almost all the time, it's going to be bigger. All right, so we have 17 factorial on top, 7 and 10 factorials on bottom. We can actually choose to write the 17 out to the 7 or the 10. I usually write it out to the biggest one because I can stop faster. So I'm going to write mine out to 10. So we have 17, 16, 15, 14, 13, 12, 11, and 10 factorial. So the 10 factorial will match. And then we have 7, 6, 5, 4, 3, 2, and 1. Okay, so just seems so cramped in there. We can cancel our 10 factorials first off. Yes, Isabel.
Could the 7 and the 14 not simplify to 2 like the last one?
Yes, in fact, we'll do that. So not even the 7 and the 14, but if you want, you can do the 7 and the 2 to make 14 to simplify to the 14. So sometimes it's easier to look for single divisions, some of our bigger values that we're going to encounter in the next problem we will. Sometimes we see pairs that pair up really nicely and work out to do that too. So I'll start with that one. So 14 can cancel with the 7 and the 2. What else do you guys see?
3 and 5.
3 and 5. You bet. 3 times 5 is 15. That cancels with my 15 on top. Now what?
4 and 3, or 4 and 12, leaving a remainder of 3.
Okay, so we can do that. I'm actually going to do the 4 and the 16. The only reason I am is because the 6 will go into the 12, but it won't go into the 16, so it's just a little bit cleaner.
I completely missed that,
Yeah, so it wouldn't hurt anything. It would just make it messier looking. So I'm going to do the 6 with my 12 to give me a 2, and then my 4 with my 16 to give me a 4. Okay, so I mentioned last time that you need to be really careful that you don't lose pieces. Even the best of us will lose pieces from time to time if we're not being extra careful. I lost a piece in a notes. It happened like Friday. That recent, isn't that crazy? Yeah, so we want to be careful. I'll write them out. You're welcome to just be careful as you're typing them in the calculator too, of course. I have a 17 and a 4. So we'll use a different color. I've got the 17 and the 4. And then working our way down, we have 13, 2, and 11. So 13, 2, and 11. And we want to make sure that we've got everything on top and everything on bottom, and I think we do. Let's grab calculator. What do you get if you multiply out all of these values?
19,448.
Yes, you guys are both saying it good. 19,448. These are the selections that she can make. That's a lot of selections, right? And we all say, good luck, Julie. There's a lot of things to pick from at this point. Good luck. Okay, any questions? Yes. Okay.
What's the difference between selections and ways?
So it likes to use the words a lot of times selections and arrangements. So selections means it's like you're picking it up and they've got a handful of it. So these are the handful of classes she's going to take. The ways would be the order in which she takes them. So when we hear the word ways or arrangements, we're talking about the order that happens in. Yeah, that's a good question. Okay, the next question we're going to do actually has 8 parts, and it all hinges on cards. So I'm going to take a very step back approach and make sure that we all understand all the details that we're going to need about cards in order to do these types of problems, and maybe even a couple extra details in here because I can't remember exactly what your questions ask inside of my math lab. So if you don't know some of these details, you might want to jot them down as I go, or if it's something you just haven't used in a while and you're like, oh, I might forget that, feel free. Okay, so we're going to be working with a standard 52 card deck. In a standard 52 card deck, there are 26 red and 26 black. It's half and half. There are 4 suits. Diamonds and hearts are your red suits. Spades and clubs are your black suits.
Wait, we said it one more time.
Yep. There are 4 suits. Diamonds and hearts are your red suits. Clubs and spades are your black suits. Each suit has 13 cards in it. So there's 13 hearts, 13 clubs, 13 diamonds, 13 spades. Those 13 cards, some of them are number cards. They start at 2 and they go to 10. So there's no number 1 in a standard deck, 2 to 10. And then after your number cards, you have face cards. So your face cards are Jack, Queen, and King. Every suit has one of each of those. And then it has an ace. Depending on the types of games you play, ace might be considered the highest card, or it might be considered the lowest card, or it might have the ability, like in blackjack, to be either one, depending on what's most advantageous to you as the player. Okay, so ace does not count as a face card, and it does not count as a number card. It is a unique, individualized, like it's got its own description. Okay. Couple different things to make note of. There are several different kinds of hands. You can talk about a hand having all the same suit. That means all of the type of card is matching, like it's all diamonds or all spades. You can talk about the cards being all the same type of card, right? Like they're all jacks or they're all sevens or something like that. So you can talk about hands like that. You can talk about having a full house. We're going to do a full house one. Full house means it has 3 matching numbers of one thing and 2 of the other. And I don't necessarily mean numbers, but matching value cards. So it could be like 3 kings and 2 sevens. That's a full house. 3 of one and 2 of another. And then another one that you might see come up, it's not going to come up in language in our problems here, is a flush. A flush means it's all of the same suit. Okay, so if you have like a diamond flush, it means it's all diamonds. If you have a royal flush, it means it's all the same suit and it's the highest 5 cards. Very rare. So you go from ace down to 10 of, say, hearts or spades. Okay? So we're going to look at the number of ways we can have certain types of hands show up when we have certain conditions placed upon us. The first one we're looking at is just any hand at all. Like how many different hands are there when you play a game that has 5 cards in it, like like poker. So we have, let me say one more thing. Sorry, forgot to say this. When you are working inside of a game, and I don't care whether the game's poker or whether it's phase 10 or whether it's old maid, somebody deals out the cards, and then what do you generally do when you get your cards? You look at them, you sort them. Okay, so you change the orders around to whatever makes sense for the game you're playing, right? If you're familiar with phase 10, it depends on what hand you're in as to which order you might put things in even. So sorting things after you get them is a standard procedure in most games. So the fact is, it doesn't really matter what order they came to you in, you just changed it, right?
There's always going to be combinations.
Thank you. Good job, Joan. It's always going to be a combination. So anytime you're talking about a card game, you're looking at a combination. So everything we do on our next 8 pieces of this problem are combinations. Okay? Very good. So we're going to do a combination. We want a 5-card hand, so we're going to choose 5 cards. And how many choices do we have to pick? 52. 52. Yeah, 52 cards. So we have 52 C5. So my numerator is 52 factorial. And with combinations, I'm going to have 2 pieces of my denominator. One of them is going to be how many I pick, 5 factorial. The other one's going to be the subtraction, or how many I don't pick. So what's 52 minus 5? 47. These numbers are considerably larger than most of them that we've done these problems with, even than last time. I think the biggest one we saw last time was like a 20 factorial or something like that. So we definitely don't want to actually calculate things like in the numerator and the denominator separately. It generally gets a little bit too big. So our reducing that we've been practicing is going to become really important on these. So I'm going to write my 52 out to 47. So 52, 51, 50, 49, 48, and 47. And then in the denominator, I have that same 47. And then I'm going to write my 5 out. 5, 4, 3, 2, and 1. Just like before, the 47s will cancel. And I'm not going to, as typically, especially with the 52 involved, going to find pairs that multiply to something on top. But you can still reduce things. So tell me a reduced step that you see. 50 and 5. So 5 and 50 makes a 10 on top. What else?
Two and 48.
Okay, 2 and 48. So what is 48 divided by 2?
24.
24.
And then divide by 3 and get a.
You could. Okay, so if we divide 24 by 3, we could get 8. There's other arrangements you could divide, but that one works just fine.
And then you put the 4 and 9 and get 0, I guess.
Fabulous. So then 4 divides by, or 8 divides by the 4 and gives you a 2. That'll work. So what do we have left? Okay, so we have 52 at the beginning and 51. I have 10 and 49. And then 2. I think that's the last one, isn't it?
Simplify your math down to just do 10 and 2, 20.
You could, and if you want to, that's fine. Your calculator will do it for you too, so either option would be great. Multiplied out, what are we going to get on this one?
2,598,960.
You're right. And I think this is part of the reason why there are so many card games that use a standard deck. That's a lot of hands, which means you've got a lot of ways that you can end up passing out the cards, different things that can come up. And this is a combination. This isn't even a permutation, right? If it were order didn't matter, it'd be even bigger, right? If the order mattered. Because the order doesn't matter, it's actually smaller than it could have been.
I've heard that like whenever you shuffle a deck, you're basically doing a completely new hand. It's never been
Yeah.
done before because it's
So big. Yeah, there's so many. Okay, so this is our sort of comparison to everything else. There's 2.5-ish million ways of dealing a hand of cards. We're going to start restricting the type of cards we're looking at. So here's our first example. This is just going to be a hand that's all red. Okay? So you might think, okay, well, I eliminated half the cards. Does that eliminate half the hands?
No.
The answer is no, and we're going to see what happens when we try to look at that. So instead of choosing from all 52 cards, I'm only selecting from 26. So this is now 26C5. So 26 on top, factorial, and a 5 factorial. And then what's my other piece on bottom? 21. 26 minus 5, 21. Okay, so good? So we'll write our 26 out to 21. And then we have our 5, 4, 3, 2, and 1. Okay, 21's cancel. 21 factorials cancel. What else cancels?
5, 25.
Okay, 5 and 25, leaving me with a 5.
4, 3, and 2 cancel.
Good job. I was wondering if anybody would see it. 4 times 3 times 2 actually is 24. And if you don't see it all, it doesn't matter. It's fine. You'll get all the pieces canceling individually. So yeah, it's 24. So we have, working our way down, 26 times 5. 23 and 22.
65,780.
Yes, you're right. 65,780. It's still a lot. 65,000 is a big number. But it's nowhere near 2.5 million, right? It isn't. So your number of hands decreased substantially when we decreased by half the deck. Okay, are we good so far? Okay, now we're going to take a look at having a hand that has all hearts. So again, remember I called that a flush. A hand with all hearts is a flush. So how many hearts do you have?
13.
13. So we're choosing from 13 now. So again, we've kind of decreased the deck by half from the 26 we had before. So 13 on top and 5 on bottom. What else is on bottom? 8. 13 minus 5 is 8. So we'll write this out. 13 times 12, 11, 10, 9, and 8 factorial. And then 5, 4, 3, 2, and 1. Okay, 8s go away, 8 factorials. What's next?
4 and 3 with 12,
Okay, 4 and 3 with 12.
and 5 and 2 with 10.
5 and 2 can go into the 10. So we're left with 13 times 11 times 9, which is
287.
1,000. Did you say 1,287?
Yes.
Good. Yes, this is the number of hands for this one. That's not real common, right? If you were sort of ascribing like value to the fact that how likely is this to occur, the answer is sort of not likely, right? 1,000 ways out of the 2.5 million, not real likely. Now, let me also mention that let's say that this didn't just say a hand of all hearts, but it just said any kind of flush, a hand that all matched in any of the suits, right? They just had to be all the same suit. Well, it means there's 1,287 hearts that do this, hands of hearts. There's 1,287 hands of spades. There's 1,287 hands of clubs, and there's 1,287 hands of diamonds. So how many would there be, relatively speaking? Like, what would you have to do to figure out what there would be?
Okay, 287 times 4.
Yeah, 1,287 times 4, right? Because there's 1,287 of each of the 4 suits. Okay? Hands of all jacks.
That's gonna be 4.
There's, say that louder. There's only 4. And how many are supposed to be in my hand?
5.
Mm-hmm. So what's the answer? 0. Okay, there are 0 hands of all jacks. But you could, which is our next question, get a hand that has 4 jacks and something else, right? This is yes. Okay, good. Yes, we could have 4 jacks. That would be all right. We could do that. So we could have 4 jacks. So there are 4 jacks to pick from, which is what you guys identified before, and we're choosing all 4 of them. This is going to feel like a funny thing to write down when you see what the answer is, but just humor me for the moment, and we'll see how it works out. But we need another card, right? How many cards are there left to pick from?
A lot.
48. Where'd you get 48 from, Trey?
There's 52 total.
Yeah, 52 total. So 52 minus my 4 gives me my 48, and I need to choose one of them. So we're going to find 2 different combinations, but both of these combinations are a little bit funny. We haven't seen it happen yet, but they're both a little bit funny. So this one would be 4 factorial on top, and I have a 4 factorial on bottom. But what happens when I subtract 4 minus 4 here?
0.
I get 0. So my other factorial on bottom is actually 0 factorial. So if you haven't yet had a chance to watch the video, you don't know the answer to this, but those of you who were in class last time who have, what is 0 factorial? It's 1. So the 0 factorial in the denominator is defined to be 1. So that'll be okay. It'll just be a number 1. We'll get back to that in just a second. Let's look at our 48 over here. So I have 48 on top, factorial, and I have a 1 factorial. What else do I have in the bottom?
44. No, 47.
47.
So stuck on 4.
Yeah, no worries. 47 factorial on bottom. Okay, so as I write these out, do you see what happens with my 4 factorials here? They're going to cancel. And the 0 factorial is 1, so this whole expression is 1. And that should sort of make sense. There's only one way to get all 4 jacks. You got to get them all 4. Right? When the order doesn't matter, right, you just have to be getting all 4 of them. Over here on the second one, so this is actually the number 1 at the beginning now, we have 48 on top, and so we'll write 48 times 47 factorial over 47 factorial times 1, and what happens?
47 is canceled.
And so we're left with just 48. But again, that should sort of make sense. I have 48 to pick from, and I can pick any of them, so there's 48 choices, right? So this gives me 1 times 48, or I have just 48 hands. There are only 48 hands that are all jacks. Well, 4 jacks. 4 jacks and an extra. Only 48 hands. But what does that tell you about every card, right? Like, what if I'm looking at number F, letter F, and it says 4 of a kind? So it's not just 4 of jacks, but it's 4 of jacks, or 4 of sevens, or it's 4 of aces, or it's 4 of threes, right? It's 4 of any of those. How many of those are there?
48. Wouldn't it all just-
No, not 48. How many
Oh,
different
4 by 9.
numerically,
Wouldn't you just divide 52 by 4?
which is what?
I don't know. Very close to-
Isn't it 13?
It is 13, you're right, Bella, yeah. So there are 13 different sort of value cards, right? If you think of faces and aces and numbers, there's 13 of them, right? So I have 13 different cards. Okay, ignoring the colors and the spades and clubs, ignoring all that, there's 13 different numerical values, right? Think about playing the game of war, where it's just whether or not your number's bigger, right? You get the cards if it's bigger. There's 13 different values times what I had before, which is really 4C4. We already did it, but I'll write it out in case we had not already done it. And then 48C1. So the 13's coming from the fact that there are 13 different valued cards. Oops. There we go. And then the 4C4 says I select all 4 of whatever I'm picking, and then I select one more random card. So I already found those, so I'm not going to find them again. But this first one's still 13, that middle one's 1, and the last one's 48. So 13 times 1 times 48 is what?
624.
Yes. So if you're familiar at all with poker, my husband used to watch the Poker Channel. He used to watch Texas Hold'em and all that kind of stuff all the time. I remember that from, it's been a while back, but he used to watch it all the time. And they would display like percentages of how likely people are to win on the screen. And they make those decisions based on how likely hands are to pop up, right? There's only 624 of these hands, which means if I had 4 of a kind and you had a flush over here, of which there were, oops, I skipped back too far, of which there's 4 times this number, it's about 5,000 hands. There's about 5,000 hands that are flushes, but there's only 624 hands that are 4 of a kind. Then my 4 of a kind, because it's more rare, would win. And that's how the rules are designed, and that's how they make those decisions. It's less likely to happen, therefore it is a more desirable outcome. It's the winning hand. Does that make sense? Okay, we've got a couple more. We're going to do the full house. So in a full house, I mentioned this before, I'll mention it again, we need 3 of one value card and 2 of another value card. So we established on the last question, how many different value cards are there? 13. There are 13 value cards. And of those 13 cards, of those 13 cards, I pick one of them. So this is why it's 13. And then I need to select from the 4 cards that there are, I need 3 of them. Okay, so let's pretend that for a moment I selected a 6. Well, there's 4 6s and I want to choose 3 of them. Once I've picked 6s or whatever, I can't pick them again because there's not enough cards left, right? I need to pick another valued card. So if I've already picked one of the 13 value cards, how many value cards are left? 12. Right, I already picked one, so there's only 12 left to pick from. And whichever one of those I pick, there's 4 of them. But a full house and a hand of cards that I'm working with anyway, I only have 5 cards, so I will only pick 2. So this one's 4C2. So again, the 13 and the 12 come from the fact that I have to choose the value card. 12 is happening because I've already chosen one of them and have eliminated it from being chosen again. And then the 4C3 and the 4C2 are because I'm choosing 2 cards and 3 cards of different values. Okay? So we have the 13. And then we have 4 factorial over 3 factorial. And what else will go on the bottom of this one? Right here. 1 factorial. It's not very exciting, but that's what goes there. And then I have a 12. And then I have a 4 factorial. And what's the denominator for this one?
2.
2 factorial and another 2 factorial. Right? The number I picked and the number I don't. Okay, so the 13, the 12, if you want to like put them at the front and ignore them for the moment, you could. I'll just leave them where they are. But I have 4 times 3 factorial so that it cancels with the 3 factorial on bottom. This ends up selecting or giving me the number 4, right? I have the 12. And then on this one, I'll write the 4 down to 2. So I have 4 times 3 times 2 factorial over 2 factorial and 2 times 1. These numbers are really small. If you just multiplied it out, it would all be good to go. But just for consistency, I'll keep doing it that way. So the 2 down here will reduce with the 4 to give me a 2. So the values to multiply are 13, 4, 12, and 2. Oh, I missed one. And 3. I felt like that wasn't enough. 2 and 3. What do you got?
$1,248.
Try again.
Oh,
I think it's bigger.
I forgot the 3.
Do you forget your 3? Okay.
3,744.
3,744 hands. And that's not very many, right? I mean, compared to the 2.5 million. But it's more than this one, right? So getting 4 of a kind is better than getting a full house. The full house, however, is better than the flush. Because remember, this is not just this is a single heart flush. And I have 4 times this many of the total any flushes. Okay, so a full house is actually more rare, which would mean that it would be the winning hand compared to the flush hand. Okay, we're just going to do a random one here at the end, not because this is anything special, but because I want you to see that it doesn't have to be anything special to make the calculations. Okay, so it says that we're going to have 2 black cards, 2 diamonds, and a heart. Just a random assortment of things. Okay, so how many black cards are there?
26.
26. And we're going to choose
2.
2. How many diamonds are there?
13.
13. And we'll choose 2. And then how many hearts are there? 13. And we'll choose 1 on this one. The last one was 1. So we have our 5 cards. Okay, so we're going to process this just like the others. We have 26 factorial on top. What's on bottom?
24 and 2.
24 and 2. Good. Next one, 13 factorial on top. What's on bottom?
11 and 2.
11 and 2. And the last one's another 13 on top. What's on bottom? 12 and 1. And all of those, of course, were factorials. Is everybody good? Okay. So we've got 26 times 25 times 24 factorial, where we'll stop for the 24 on bottom. And then I have 2 times 1. So these will cancel. I'll come back and cancel more in a minute. The next one is 13 times 12 times 11 factorial. So my 11 factorial, and then I have 2 times 1, and the 11s will cancel. And then 13 times 12 factorial, where I'll stop. I have 12 factorial times 1, and the 12s will cancel. Okay, I'm going to shrink everything just a little bit, so I'll have just a tiny bit more space. All right, so what else is going to reduce in my first fraction?
13, or meaning the 26, the 2 can go to the 26 and 13.
Yep, the 26 divides by 2 to give me 13. How about in the middle one?
2, 12, 6.
Yeah, the 2 will divide the 12 and give me back a 6. So I end up with 13 times 25 times 13 times 6 times 13. Did I get them all?
Yes.
I think so. And how many hands would that give me?
329,500.
Yes, a lot, which is why it's not a very good hand, right? There's lots of them that look something like this. Okay, so if you take a look at your class schedule right now, we have finished sections 10.1 and 10.2 and 10.3. And we have homework on this due on Thursday at midnight. Because on Friday we don't have class anyway. It's Good Friday, and I don't want you having to do any of this on Good Friday or through your Easter holiday. So what do you think is going to happen on Wednesday? No class. We're caught up to speed, so we won't need to have class on Wednesday. So enjoy your Wednesday time off. Make sure that you get your homework done by Thursday, though, all right? Thursday at midnight. And waiting until Thursday at 10 o'clock to email me and ask me questions is not a good plan. Not a good plan.